Hello everyone. Welcome to the lecture series on ARM microcontroller and embedded systems with the subject code of 17EC62. Myself Rohini Kallur, Assistant Professor, Department of ENC from KLSPTIT Halia. In the last lecture, we have learnt about the different domain specific examples of embedded system, where we have learnt about the two examples. One is washing machine and the second one is automobile, which is considered as a domain specific example, and we have seen the in and out of the washing machine and how it works. And today's lecture we will be covering module 3, that is hardware and software co-design and program modeling. For this you need to be referring to the 7th chapter and 9th chapter of the K-Shibu text. So here hardware and software co-design and program modeling is, in a traditional embedded development approach, the hardware software partitioning is done at an early stage, and engineers from the software group take care of the software architecture development and implementation, whereas engineers from the hardware group are responsible for building the hardware required for the product. So when there is less interaction between the two teams, there was a problem with the design or the embedded system which was coming into a commercial market, and because of this the time to market was taking more time. So because of this the co-design process came into existence, and co-design means the hardware team will generate its hardware according to the requirement of the process software team, and software team will write the program according to the hardware requirement of the hardware team. So in between conversations between a hardware team and a software team, what will perform a integrated work which will give me a better output compared to the traditional one. So here in this lecture, we'll see what are the fundamental issues in a hardware and software co-design. When we try to solve this problem in real life, we will be coming across multiple issues. The issues may be selecting a model, which model to be selected, and selecting an architecture, and then the last one is partitioning a system into hardware and a software. The first and foremost what we have is selecting the model. Selecting the model is a first issue what we will consider in a hardware software co-design. So what happens is the models which are used for capturing and describing the characteristics will be considered here. A model is basically a formal system consisting of objects and compositional rules. It is hard to make a decision on which model to be followed. So most often, the designers switch between a variety of models for requirement specification to implementation aspect. So, the objective varies with each phase. That means when it is in a specification phase, the model will be different, and when it is a implementation phase, the model will be different. So, when the model shifts from a specification stage to a implementation stage, at that time, we need to be making a proper decision that whether we want to switch to a model which is capable of capturing the system structure, or we want to retain in the previous one which is being used. So the second one or the second issue is selecting an architecture. Selecting an architecture means the model whatever we have selected in the earlier stage, it only captures the system characteristics and does not provide any information on how the system can be manufactured. So the architecture specifies how a system is going to implement in terms of number and types of different components and interconnection between them. So here we'll be having the different components whatever we have that are controller architecture, data path architecture, CISC, RISC, and VLIW, SIMD, and parallel processing architecture. These are the different architectures which will be selected for one particular embedded system when I try to select it. So in the first architecture, what happens is the controller architecture what I have, it will implement the finite state machine model using a state register and a two combinational circuits. So what happens in the controller architecture actually is we will be having a FSM using a state register and two combinational circuits. So a state register always hold the present state, and the combinational circuit that is implemented will be holding the next state and the output. So the next type of architecture is data path architecture. Data path architecture is best suited for implementing the data flow graph model, where the output is generated as a result of set of predefined computations on the input data. The data path actually represents a channel between input and output, and in a data path architecture, the data path may contain registers, counters, register files, memories, and ports along with high speed arithmetic units. So the ports that connect data path to multiple buses will be having here most of the time arithmetic units coming into picture, which will be giving me a better and high performance. Then coming to the next data path, which is finite state machine data path. Finite state data machine data path architecture, that is FSMD architecture, it combines the controller architecture with a data path architecture. It implements a controller with a data path. The controller always generates the control input, whereas data path processes the data. The data path contains two types of IO ports, out of which one acts as a control port for receiving and sending the control signals from and to the controller unit, and the second IO port interfaces the data path with the external world for the data input and data output. Normally, the data path is implemented in a chip, and the IO pins of the chip acts as a data input output ports for the chip resident on the data path. Next, we have the next fundamental issue, that is selecting a language. Selecting a language means a programming language captures a computational model and maps it into architecture. So there is no hard and fast rule to specify this language. It should be used for the capturing of this particular model. So when I say a language, the programming languages like C, C++, C#, Java, or the machine languages like VHDL, System C, Verilog, all these are used for software and hardware implementations respectively. So when I try to select a language for an embedded system, a single language can be used for capturing a variety of models, and certain languages that are good in capturing certain computational model that can be selected. So the only prerequisite in selecting a programming language for capturing a model is that the language should be capture the modeling or the embedded system model easily. Then when we talk about the partitioning system requirements into hardware and software, we have seen that when I try to incorporate the changes in the hardware as well as software, then initially we need to make a decision that which part of my embedded system should be done under the hardware and which part should be done under software. So we will be having this bifurcation or this partitioning done for the requirements of hardware and the software. And what happens is when I try to bifurcate or partition like this, it is a tough decision to make the task and to figure out which one will be opt. So there will be hardware software trade-offs that are used for making this decision on hardware and software partitioning. Yeah. Then selecting a model. Selecting a model, we have said that we will select one particular model. So what are those different models? That is the concept here. So the computational models in the embedded system design are data flow graph model, state machine model, concurrent process model, sequential program model, object-oriented model, and so on. We'll see one by one. So the data flow graph model, it is the data flow graph model translates the data processing requirements into a data flow graph. It is a data-driven model in which program execution is determined by the data. This model emphasizes on the data and operations on the data, which transforms the input data to output data. Indeed, the data flow graph is a visual model in which the operation on the data is represented using a black circle and the data flow is represented using arrows. An inward arrow to the process represents an input data and an outward arrow to the process represents an output data from the DFG. Embedded applications show us that for DSP applications or wherever I want a application to be generated, like addition, subtraction, and so on, at that time I'll be selecting a node that is a data flow node which will be using as an adder or a subtractor or a multiplier or so. So we have a example here where there are 5 equations. The output of them are x, y, z, x, x. The first x which will give me a plus b. So from variable a, I have the inward arrow to the data flow graph node which has a adder, and for b also I have an inward arrow, and these two are acting as an input. And from the node I am getting an outward arrow that represents x. So x is equal to a plus b. And similarly, the second output what I have is z. So that z is equal to a plus b, which is represented as x, and I have another input d, that is z. So z is equal to x plus d. As you can see in the third equation, it is z. And the second equation is a, c. The two are multiplied because the data flow graph node what we have is a multiplier and the output generated is y. And I have c coming in to directly to a adder, and the output of a plus b, that is represented as x, is generated and it is giving me a capital X. So last equation x is equal to x plus c, that represents this data flow graph model. And in the last figure we have output x which is represented by output y, that is a multiplied with c, and you will be subtracting it because the data flow graph node what we have is a subtractor. So x is equal to y minus t. So we'll move to the next one, that is control data flow graph, that is CDFG. In control flow graph what happens is we will be having the data flow graph model. Along with this there will be a conditional program execution. In the previous data flow graph model, it was a data driven and it was executed and controlled by the data, and it does not involve any conditional statements. Whereas this CDFG diagram what we have, this will have the conditional program execution, and the CDFG models will always have data operations as well as control operations. This uses CDFG data flow graph as an element and conditional statements as a decision makers. So the example is, say I have an example program here, function 0, that is this one. If while condition 1 means if this condition is true, then it will move to function 2. If the condition is false, then it will move to function 3. So what happens is every time the condition will be checked, and if the condition is yes, if the condition is true, then only it will be moving to the next function, otherwise it will be moving to the function 3. So for today's lecture we have learnt about what is a model, How do I select a model? What is an architecture? How do we select an architecture? What is a language? And what are the different computational models? In the computational models, we have seen two. One is called the data flow graph model, and the second one is a control data flow graph model. And rest models, whatever we have in the list, that will be considering in the next video. Till then, thank you.